Okay, so we will begin today by revisiting the rocket data that I showed you on the board about a week ago. And so I will walk you through the analysis in R. The data file is posted on Learn. It's called Rocket. It's a CSV file. Okay, so as I mentioned, the data comes from experiments in the late 90s. And so we're going to first load this into R. Okay, so as a reminder, I have this file in the same folder in which I started R. So this should work fine in terms of loading in the data. But if it's not the same folder, you can use R's set working directory, and then you would put whatever folder where you stored the file before loading it in. Okay, so now that we have the data loaded in, let's just type it and see what's in there. So this is the data I mentioned before. So the response variable is thrust, and then the two predictors are the nozzle size and then the propellant to fuel ratio. So those are listed in these two columns. So in this case, nozzle, there's only two values, small and large. So I've coded large as 1 and small as 0. And later today, we're going to talk about, in general, how we would go about handling what we call categorical explanatory variables. Okay, so in this case, it's just two possibilities, large or small, so 1 or 0 works fine. Okay, so when we did simple linear regression, the first thing we did before fitting any models is to plot the data. And so here, we should again plot the data. Now, of course, once you have multiple variables, it's not as straightforward to plot x versus y. And in fact, generally, we'd have to do it one variable at a time. So that's what I'm doing here. So in terms of scatter plots, I would have to do one variable at a time. So I'm going to do nozzle against thrust and then propellant ratio against thrust. And so here's a way to set up our plots in R. So this MF row parameter, so if you set this first, then you can put multiple plots in one on one screen. And so here I'm dividing it into 1, 2, so one row and then two columns. Okay, so this will allow both of these plots to show up together. Okay, so let's go ahead and make this plot. And so I've used YLab and XLab to label the axis. So on the left is the first one is nozzle size versus thrust, and then on the right is the scatter plot for the propellant ratio to thrust. Okay, so that allows us to see that indeed it looks like when the nozzle size increases, thrust increases. And then as for to fuel ratio, it looks like it might be a little bit of a decreasing relationship, but it's not, it doesn't appear to be very strong. Okay, so with the plots made, let's now fit the model. Just like with simple linear regression, we use the LM command to fit the model. And so now to remind you of the syntax, so the first input here is the formula object. So on the left is the y, or the response variable, and then on the right we put an expression for the explanatory variables to put in the model, and we use the plus sign because we're fitting what is called an additive model. So it's equivalent to our formulation for multiple linear regression. So this will fit in intercept term plus beta 1 nozzle and then plus beta 2 propellant ratio. So in terms of syntax, you can just, if there's many variables, it can be shorter to just put the data object at the end, so it will automatically read these columns from the rocket data frame. Otherwise, we could just do rocket $ thrust and so on, and that would give us the same results. Okay, so let's fit the model, and then as before, we'll use the summary to see the estimates that R gives us, along with standard errors and then the p-values and so on. So the format of this is pretty much the same as for simple linear regression. We have the estimates followed by their standard errors, followed by the t-statistic, and then the p-values. And so that reminds us of what we learned about the estimates for the beta vector. Okay, so we have beta hat, and then we can obtain the standard errors of beta hat from the estimated covariance matrix. Okay, so the rest of the layout is pretty similar to simple linear regression. At the bottom, there's an estimate of the residual standard error. So that's our estimate sigma hat. And then it will list the coefficients by according to the names that we have for the variables, so we can tell which one is which. Now, just to illustrate what we've done, since we did a lot of linear algebra, is it would make sense to try doing this manually as well. So for a couple of reasons. First, you can see how to set up the X matrix and literally see what the X matrix looks like, and also how to carry out linear algebra operations in R. Okay, so the first ingredient to that is to define a matrix for X. So this is the model where y is X times beta and then plus epsilon. Okay, so we need to set up the matrix X with all the columns for the predictors. Now, if you remember, we need to add a column at the beginning of just ones for the intercept, so that will capture the intercept term when we do the matrix multiplication. So I can use the rep command so this just repeats the value 1 12 times. Okay, so this creates, so if I just do this part, you'll see that this just creates a vector of 12 ones. Okay, and then so I'm going to need 3 columns in this matrix X. The first column will be all ones, so I'm going to use this vector of ones for my first column, and then I'm going to add the columns for the other 2 predictors. Okay, so this is, as you recall, pulls out the column nozzle in the rocket data set, and then same thing for propellant ratio. Okay, and so we want to put these 3 as columns and put them together as these 3 as columns in our matrix. So we use a cbind. Okay, so this binds together these vectors, treating each of them as a column. All right, so that gives us our X matrix. And so again, let's just type to see. Indeed, we have the vector of ones, and then we have x1 and then x2. Okay, and then likewise, we can set up our response vector, and so we can just view this as a one column matrix. So that's taking the values in thrust and then setting it up as a 1 column matrix. So that gives us a y. Okay, and so now we have X, we have Y, and so now we can solve our least squares equations for beta hat. Okay, and so this line gives us syntax for how to do some basic matrix operations in R. So you notice that there's this symbol, this operator. So percent sign and then the time sign and another percent sign is what does matrix multiplication in R, okay, so as opposed to simply the times sign. Okay, so we need to explicitly use this as the matrix multiplication operator. Otherwise, R will simply take all the elements and do element-wise multiplication. In this case, we're going to do matrix multiplication, so we use R's matrix multiplication operator. Okay, so that's first thing to note. Second thing to note is we need to do transposes. For example, we need to do X transpose X. So we can use the T command to transpose the X matrix. So now we know that this first piece means X transpose X. Okay, so there's that part as well. And then finally, we need X transpose X inverse, right? So to take the inverse, we can use solve. So we put that matrix inside solve, then this will give us the transpose of this matrix inside. So in other words, now that we can read this expression as X transpose X inverse X transpose Y. Okay, when that's exactly the form we derived for least squares estimates. Now, if for whatever reason, like we missed a transpose or something, and the matrices we're trying to multiply are actually not conformable, then R will spit out an error, and then we can check that indeed all the matrix dimensions are agree, and that it's actually valid to do the matrix multiplication. Okay, so let's calculate beta hat, and then let's print out this vector of estimates, and so that's down here, 473, 16.7 minus 1.09, which we see matches the estimates in the LM output. So that's beta hat. Okay, so that's how we could manually code up those matrix operations to calculate our parameter estimates. So in a similar way, we can also manually calculate our sigma estimates, just to remind ourselves of the formula that we derived. So again, the sigma hat is in our output is 2.655. Okay, and so again, we can manually calculate it. So we can do it in a couple steps. So first, remind ourselves of the fitted values. So the fitted values is X times the estimates of beta. Okay, so we do the matrix multiplication X times beta hat. So that gives us mu hat. And then the residuals, by definition, are the difference between the response and the fitted value. So we can do y minus mu hat, and so that gives us the vector of residuals. And there are 12. There are 12 of them because we had 12 observations in our data set. Okay, and so how do we get from the residuals to the estimate of sigma? Okay, so according to our formula, we can do E transpose times E in vector form. Okay, so that's here. So E transpose E, and then we have to divide by the residual degrees of freedom. Okay, so how many residual degrees of freedom? Well, it's n minus p minus 1, where p is the number of predictors, and then 1 is for the intercept term. So we have 3 betas here. We have beta 1, beta 2 for nozzle size and propellant ratio, and then we have beta 0 intercept. So we fitted 3 model parameters, so 12 minus 3, so we have 9 residual degrees of freedom. So we take E transpose E divided by 9, so that gives us the estimate of sigma squared, and if we want the estimate of sigma, we take the square root of that, and so that's why I have this expression for sigma hat. Okay, so let's do that calculation, and then indeed sigma hat is 2.65, which matches the output that we saw from R's LM command. Equivalently, we can simply also just do, remember it's just the sum of square residuals, so another way to express the same thing is to take all the residuals and square them, so E squared, and then sum them up, so it gives us sum of squared residuals, divide by the residual degrees of freedom, that's 9, take the square root, so both of these are equivalent ways this is for the same calculation. Okay, so that is sigma hat. All right, so So that is the how we could manually do it, and it's good to see at least once because this is how we derived the estimates with matrix algebra earlier, and so it's good to be able to see how to carry out all those calculations using those formulas directly in R. Of course, in practice, I would recommend for data analysis to just use the built-in LM command because R carries all these things out automatically. Okay, there's a question. Why did you use the solve function? So the solve function is one way to get the inverse. So it's not named very well, but solve of the arguments gives the inverse of the matrix inside. So I agree. It's not. When I first saw it, I thought, okay, that's not a very descriptive name, but in fact, I believe it's named for solving linear systems, and it just turns out if you just solve on a matrix, that gives us the matrix inverse. Okay. Okay. So now we have the point estimates. So we have beta hat, we have sigma hat, and so next thing we looked at was the estimators. So the corresponding estimators of estimator beta hat has a normal distribution with mean beta and with the covariance matrix. Okay, and so it's multivariate and normal. So what is the covariance matrix estimated covariance matrix for beta hat? And so to extract that, we can use VCov, so that stands for variance covariance, and we can put in simply the model we saved earlier. So I saved the output of LM into the variable M1. So if I just take VCov, variance covariance of the model object, that will give me the covariance matrix for beta hat. Okay, and it has everything labeled. So as we expect, the covariance matrix is symmetric. Okay, so you have the diagonal elements, and then you have the covariance terms between the various betas. Okay, and so generally, I mean, as we described in the derivation, often we're most interested in the standard errors of individual parameters. Okay, so this is the entire covariance matrix, and so we said that the diagonal elements, so 22.2, 2.35, 0.88, these represent the estimated variance for the individual betas. Okay, so 22.2 is estimated variance of beta 0, and then 2.34, and then 0.88. So those are the estimated variances for those corresponding betas. And so if we are mainly interested in looking at let's say confidence intervals for individual parameters, we only need the diagonal elements. So you can extract the diagonal elements by using the diag command. So if you put the matrix in, so VCov of M1 gives us this matrix, and then you put it inside the diag command, that'll extract the diagonal. Okay, so you get the diagonal elements, and the standard errors are the square roots of the estimated variance. So I take the square root, the vector that gives us the standard errors for these three parameters. Okay, and so 4.7, 1.5, 3.94. Again, you see that matches the model output, the values we see in the standard error output here. Okay, and then likewise, we can also do this calculation manually. So according to what we derived, what's the estimated covariance matrix? Well, it's sigma squared hat times the x transpose x inverse. Okay, so that's the expression from our notes. So if we want to get the standard errors manually, so we need to do sigma hat times the square root of the diagonal elements of X transpose X inverse. Okay, so that's what this expression gives us. Okay, so this, again, this part gives us the inverse of X transpose X, and we extract the diagonal elements, square root, and then multiply by sigma hat. Okay, so we do all that. That gives us the same standard errors that we had both using the extracting from the model output and also from the summary of LM directly. Okay, so there's a question, why isn't the covariance matrix diagonal 1? Okay, that's a good question. Now, we haven't so far we haven't used the covariance elements in this beta hat multivariate normal, but generally it is true that the beta hats, so the individual parameters, so here for example the estimates of beta 1 and beta 2 are correlated. In fact, this gives us the estimated covariance between them, minus 0.61. Now, we haven't used them directly yet, but I will show you how an example today for how these why these covariance terms could also be useful in application. So later we're going to talk about categorical predictors, and so that's one example of a situation where we might need to take the difference, for example, between two different betas in our model. And so if you want the variance, let's say, of the difference of two betas, then you notice that the covariance term will come into play when we try to get the standard error of differences, for example, between parameters. Okay, so in general, this matrix is not going to be diagonal, and we solved the exact form of it. It's a multivariate normal. If you look back at our notes from I guess 2 lectures ago, right? Sigma squared times X transpose X inverse. Okay, and so in general, X transpose X inverse is not going to be diagonal, and so therefore the estimated covariance matrix for the betas is very much related to that. Okay, so that again shows all the different calculations we can do for beta hat, and then its standard error, and also its estimated covariance matrix. The last thing I want to show is prediction. So that goes off what we did at the end of last lecture, is to calculate a confidence interval for either the mean response or a prediction interval for an individual response. Okay, so just to illustrate, I'm going to set up this scenario. So let's do this. Let's estimate the mean response for all hypothetical units such that we put in a small nozzle and a specific propellant's ratio. Okay, so that means the nozzle is going to take value 0, and then the propellant ratio is going to take value 5.5. Let's calculate a confidence interval for the mean response. Okay, so again, I'm going to show the automatic way using the predict function, and then we're also going to do it manually. Okay, but first we can do this using our predict function. So let me just run through the arguments. So you can plug in the model object. So that's the model we fitted, M1. And then we need to set up an argument called new data. And it has to be in the form of a data frame. So basically, we set up a data frame by typing data frame, and inside you put the variables and the values at which we want to make the prediction. In this case, we want to do prediction with nozzle equals 0. So these variable names have to match the names in the data frame we used to fit the model. Otherwise, R will complain. Okay, so we need to set the value for nozzle and set the value for propellant ratio. So these are the exact names we used earlier. So nozzle equals 0, propellant ratio equals 5.5. Put it inside a data frame and call that our new data object. Okay, and then we have to specify what kind of interval we want. So for the mean response, we use the value confidence. Okay, and then you'll see it's different when we do the prediction for an individual unit, and we also need a confidence level. And so here, let's just say we're going to do a 95% confidence interval, so we'll put 0.95. Okay, so this will give us the confidence interval for the mean. Okay, so in our terms that we derived last time, so the fit here corresponds to the estimate of the mean. So this would be like y0 hat that we derived, and then there's a confidence bound around that estimated mean. So there's a lower limit, upper limit. So it's y0 hat plus minus, and then the constant from the t-distribution times the standard error. Okay, so R calculates all of these things using that formula, and gives us the lower bound 464.8, and then upper bound 470.4. Okay, so remember that this is the estimate of the mean response. So hypothetically, the average response for any unit that had a small nozzle and 5.5 propellant ratio, this would be the estimate of all possible units hypothetically that have those characteristics in their explanatory variables. Okay, so let's also run through the manual calculation based on the formulas we saw on the board. So again, we will set up a row vector for the explanatory variables. That's what I called x0. Okay, so x0 is the row vector with the values of the predictors. Okay, so as I mentioned on the board, we started with a 1 to represent the intercept, and then we put the values of the other predictors, so 0 and 5.5, and then set it up as a row vector, so 1, 0, and 5.5. Okay, so the estimate is mu for the mean. Okay, so we call that mu 0 hat. We need to do x0 times beta hat, and then its standard error is again using the formula. It's sigma hat times the square root of x0 times x transpose x inverse, and then times x0 transpose. Okay, so that rewrites the formula that we saw on the board in matrix multiplication notation. So that gives us the standard error, and then we look up the t-distribution to get the value of c. So the value of c, we use the 0.975 quantile, and the t-distribution is 9 degrees of freedom. Remember, 9 is the residual degrees of freedom, so that gives us all the ingredients. So this is mu 0 hat, that is the estimate, okay, and then we have plus the constant, so this is c, so it's like 2.26, and then times the standard error, that's 1.23, and so we can do calculate the corresponding limits. So the lower limit would be the estimate minus the c times standard error, and then upper limit estimate plus c times standard error. So we calculate those, and then I've just put that inside a vector so to match the output that we saw for the predict command. So it ordered it in terms of the estimate and then lower limit, upper limit. So I'm just putting it in the same way so that we get exactly the same values as in the output of the predict function. Okay, so that's the estimated mean response. So corresponding to that, we also have prediction interval. Okay, and so remember the key difference is in one case we're estimating the mean of all potential units with those characteristics, and here we want to predict the value of an individual unit with those characteristics. And so, as I mentioned, it's easier to estimate a mean than to estimate one individual response. So even though the estimate is the same value, the prediction interval will be wider because we're trying to give a 95% bounds for one observation with those characteristics. Okay, so the way it's done in R, it's essentially the same command. Okay, so predict, everything is the same except we're now asking for a prediction interval rather than a confidence interval. So we replace the interval argument with prediction. Everything else is the same. And in my comment here, I should, this is a typo. I'm going to change that to prediction interval because we're doing prediction for an individual unit. Okay, so we do that output, and we see, again, as expected, both of them are centered at y0 hat, which we calculated. And now you notice the interval is wider. Okay, so instead of going from about 465 to 470, it now goes from 460 to 474. Okay, and why does that make sense? Well, because we're trying to predict one individual unit. So with 95% confidence, the response for an individual unit with those X characteristics will fall in here. And so remember, there's two sources of variability. We talked about in simple linear regression. You have variability due to the estimates in the parameters, and then you have also variability due to model uncertainty, right? So the model uncertainty comes from the sigma square term, which represents variability not explained by the linear model. So we have to bake that uncertainty into our prediction interval. Okay, so that gives you intuition for why the prediction interval is wider. And finally, I can do the same thing using a manual calculation. So the only difference is this line. Okay, so the standard error has an extra 1 plus term. Okay, and so that's what we saw in the formula. So that's what accounts for the extra sigma squared that we have to account for when we do prediction for an individual unit. Okay, so we can do all this, execute all this calculation, and then you notice it gives exactly the same value. Okay, so that finishes this R demo that covers all the aspects of multiple linear regression that we've talked about up to this point. Would it be more appropriate to name mu 0 hat to y0 hat? Yeah. So I think, based on the notation I gave you, we could call this alternatively y0 hat. I mean, yeah, it's not a crucial distinction, because in this case, mu 0 hat is the estimated mean of y at that value, and so we have been using mu hats in other places as well. But yeah, when I upload the code, I will call these y0 hats to be consistent with the notation I used on the board last lecture. Okay, so with that done, let's move over now to the whiteboard, and we're going to talk a little bit about specifically how to handle categorical predictors. Okay, so just give me a moment to move the camera, and then I'll be on the whiteboard in just a moment. Okay, so we are going to talk about handling categorical variables. So in this situation, we're considering the case where sometimes our explanatory variables might be specified as being one of several categories. Okay, and so let's talk about how to incorporate them in our multiple linear regression model. Okay, so what I mean by that is, so when there are explanatory variables that have values, okay, so the values are one of several categories. That fall into one of several categories. Okay, and so we actually just saw one example of that in our rocket example. So for example, nozzle, large, and small. And so as we noticed, if there are just two categories, so large and small, so we just code one of them as 1 and the other as 0. So if just and so if just binary, we encode as 1 and 0. So that's pretty straightforward. Okay, and so then we can interpret the beta as simply the difference between large and small, holding everything else constant. Now, in the case where there are multiple, more than two categories, then we have to do a little more work to be able to use them in our multiple regression model, and that's what I want to discuss today. All right, so what if we have, let's say, three categories? Well, there's kind of two kinds of situations that we might encounter. So the categories might be ordered. Okay, so for example, you could have like small, medium, and large. Okay, so there's some sort of ordering to it. So you might expect that each of these differences to be, for example, positive. So there's some relationship between the categories, or sometimes or sometimes are not. There might not be. So, for example, we might have different colors as a predictor. So we could have red, blue, green, for example. And so, as a general approach, we have to we have to decide as follows. So whether we want to convert them into indicator variables, or alternatively, in some cases, it might be appropriate to treat them on some sort of a numerical scale. Okay, so sometimes if they're ordered, for example, small, medium, and large have specific sizes, it might make sense, depending on the situation, it might make sense to simply use the numbers corresponding to the sizes as predictors, or we could treat them as categories. Now, if they're in the case where there's no ordering, like red, blue, and green, then of course it would be the sensible approach would be to use what we'll call indicator variables. Okay, so let's make this point first, so we can convert to indicator variables, or treat as numerical if it makes sense to do so. Okay, and this part of it makes sense to do so. Of course, is very much associated with having a linear relation between y and the different categories. Okay, but let's use a specific example to illustrate. Okay, yeah. So I do have a picture. So in 20, okay, so the data comes from a study, so so here's a concrete example. So this is 2018. So maybe like some of you, I had a cup of coffee this morning before teaching. So here's a coffee. And so in this data set, it comes from the so-called Coffee Quality Institute, and so there were a bunch of trained reviewers that had to rate a bunch of coffees, and there's many predictors in that data set. So I'm just going to pick a few. Actually, I mean, to be fair, I didn't always drink coffee, and in fact, I really only started enjoying coffee when I was in Florida. And the story kind of went like this, right? Florida is very, very hot, and I decided to have an iced coffee because it was a very, very hot day, and it was nice. And then I started having more iced coffees, and so before you know it, I became quite dependent on coffee. I mean, so that's often what caffeine does. So I'm not as much of a connoisseur as these guys that reviewed these various coffee beans, but it's a very detailed data set, and I'm going to use it. I'm going to use a few more of the variables a little later, but for today, I'm just going to look specifically at one set of categorical one categorical predictor, which is the method of processing the beans. Okay. Curious how Starbucks coffee ranked. Yeah, we can. Actually, if any of you know where Starbucks coffee is sourced from, we might actually be able to find it in the data set. But let me just describe a couple of the variables so that we can use this example to illustrate the main points for today. So I'm going to extract a few. Okay, so here's extract a few variables. Okay, so let's give you a few rows, and okay, so 1, 2, 3, 4, and so on. There's over 1,000 different types of beans that were reviewed. Okay, so I'm just going to give you a couple of the variables. Okay, so there's acidity. So this one is numeric. So I'll just give an example of a numeric predictor. So some values 8.7, 8.3, 0.2, 0.4, and so on. And then there's the method of processing. So I'm not an expert in this, but apparently there's a variety of methods to use on the beans after harvesting. Okay, and so you can look up the details if you're interested. So they're called. So the one is washed, and so it's basically the wet processing method. Okay, so let's say we have two. I think the first two are washed. Use the wet method. And then there's also a natural or a dry method. And then there's this like hybrid method, so it's called a semi-washed and pumped. Okay, so if you're a fan of coffee, you can read on your own later what exactly these processes and methods mean. But suffice for now. Okay, so there's other predictors, and then at the end we have our response, which is, for example, the rating of the flavor. Okay, so these are some numbers. Okay, so that just gives you an example where we have, let's say, some numeric continuous predictors. Then we also have an example of a categorical predictor. Okay, and so let's talk about, well, how are we going to set up our matrix of predictors X. Okay, and so to make this concrete, I'm going to try to draw out an X matrix so we can see exactly how this is going to look like. So how to set up the matrix X. Okay, so let's call this first variable acidity, so it's continuous. So we'll just call this one x1 for acidity, and then we're going to have to define some variables to capture the methods. And so, okay, so here's one example. So for example, if it makes sense to do so, and I probably would not recommend this for this example, but here is one idea, right? So you could code the different categories with numbers. So for example, you could say you define x2 for the ith observation to be 0, 1, or 2, for example, and you could say, let's say 0 is dry, 1 is semi, and 2 is wet. Okay, so you could try to code it as a single variable. Now, in general, unless we're pretty sure that there's a linear relationship in this order, I would not recommend doing this. Okay, because this is not a very flexible model. For example, coding it this way would imply that there is an ordering between dry, semi, and wet, and the effect of the semi method would be exactly halfway between dry and wet. So you see, this is a very rigid kind of coding, and often something like this would not be appropriate for categorical variables that don't have a clear ordering in terms of their effect on the response. Okay, so this would be not generally appropriate unless we're pretty sure the response is linear in these values. Okay, so this is not generally appropriate unless we think the response is linear in this in these according to this scheme. Okay, so this is why often we instead use indicator variables, and so then we allow each of these three categories to have its own effect on the response. Okay, so a more flexible approach is to use indicator or dummy, so-called dummy variables. Okay, it's a more flexible approach. So an indicator or or some books call it dummy variables. Okay, so I'll leave this table here. Okay, so so how we would do that is, okay, so we can set up one variable for whether the method is, let's say, semi or not. So we encode x, so that we encode the second x for the ith observation, and put it 1 or 0. So 1 if the method is semi, and 0 otherwise. And then we can do the same thing for create a new variable x3, which is again 1 or 0 if let's say 1 if it's using the wet method, and then 0 otherwise. Okay, and so with that coded, then we can express our matrix for x. So based on this coding, all right, so it's a good practice to write it down so we see explicitly how it'll look. All right, so the first column is the intercept, so they're all ones, it's a column of ones. And then the next one, we call it acidity, so let's just put in numbers. Okay, and then the next column, we're going to put ones if it's using the semi method, and 0 otherwise. So the first 3 are not, so 0, 0, 0, 1. And the next one is whether we use the wet method or not, so it's 1, 1, 0, 0. Okay, so this is the corresponding matrix for x after having defined these indicator variables for the different categories. Okay, and so as a side note, you notice I didn't define one for dry. Okay, and in fact we don't need to. So it's, as a side note, let's briefly explain why not. Okay, so we'll put why not define one x4 to be 1 or 0 for dry and otherwise. Okay, so why not? Okay, well, again, let's this helps reinforce something we talked about in terms of linearly dependent columns. Okay, so if we were to do that, then we would have an additional column. Okay, so I think it'd be helpful just to write it out. Okay, so if we did that, we would have 1, 1, 1, 1, and then we have these numbers. 0, 0, 0, 1, 1, 1, 0, 0, and then 1, 0, 0, 0, 1, 0, right? So we follow that train of thought. Now you notice that this matrix has linearly dependent columns. Okay, so we have a vector of ones, we have vector x1 column, and then x2, x3, and x4. And with this extra column, now you notice that we have linear dependent columns, because x4 can be written in terms of the one vector x2 and x3. And in fact, specifically, x4 now could be written as 1 minus x2 minus x3. Okay, so in terms of what we said about the matrix for x, we want the columns to be linearly independent. Okay, and in particular, this matrix would not have full rank because we can write the last column in terms of the others. Okay, so that's why we do not need to code another variable for the last category because there's no new information in the corresponding X matrix. In fact, this would fail because the X transpose X would no longer be invertible. Okay, so let's note here. So we don't do this because there's no new information. Okay, and X would not be not full rank. In particular, we could say that this matrix, these two matrices have the same rank, and what is it? It's p plus 1 is 4. Okay, so this guy has rank 4. All right, so that explains how we set up categorical variables. And so now let's look at how we would interpret the corresponding estimates. Okay, so once we have this matrix for X, we can fit our model as usual. So let's write it down and talk about how we interpret all the parameters in this situation. Okay, so this part is done. Okay, so our model then, let's say that for the ith observation, yi would be an intercept plus beta 1 x I1 plus beta 2 x I2 plus beta 3 x I3, okay, because there are three predictors in this X matrix, one for acidity and then two indicator variables decomposed from the method categories. And as we explained, we don't need a third indicator variable for dry. Okay, so it's beta 1, beta 2, beta 3, and then plus epsilon I. Okay, so that's the multiple linear regression model. And so let's talk about the interpretations of the parameters. Okay, so let's focus on the regression part. So for example, if I said, what is the mean flavor, so that's the response, mean if acidity is, let's say, okay, let's plug in some value, let's call it x01. And method okay, so there's three methods, so let's run through them. Okay, so method dry would have the following mean. So if the method is dry, that means these two x's are 0. So it would be represented by is beta 0 plus beta 1 x01. Okay, so that's how we can interpret the various means, and then we can do the same for the other methods. Okay, so I'm not going to rewrite this entire sentence. The method wet. Okay, so the method is wet. That means you have to put a 1 for x3. So the mean for this one is beta 0 plus beta 1 x01 plus beta 3. Okay, and then similarly, if it's semi, then you would have plus beta 2. Okay, and so with that in mind, we can see how our estimates for the betas the corresponding estimates for the betas should be interpreted. Okay, so let's state that explicitly. Okay, so let's just write this last case. So the method is semi, then the mean is beta 0 plus beta 1, x01 plus beta 2. Okay, I don't need this anymore either. Okay, so now, these are the various means. So now we can talk about individual parameters. So what does beta 2 in the multiple linear regression model represent? Well, okay. Well, first you have beta 1, and that we can interpret in the usual way, because the first predictor is continuous. So beta 1 represents the expected change in the flavor if we change the acidity by 1 unit. Okay, so that has a standard interpretation. But let's focus now on these parameters associated with the categorical variable. Okay, so what is beta 2 then? Well, you look at these three expressions. Beta 2 is the difference between this third line. So then the method is semi and method dry. So beta 2 represents the difference in the expected flavor. You go from if you change the method from dry to semi. Okay, so this is difference between semi and dry in the expected response. Okay, and then of course, holding acidity constant. Okay, so that's implied here. And similarly, we look at beta 3. Beta 3 is the difference between wet and dry. So it's okay, and then blah blah blah, holding other variables constant. Okay, so in effect, these parameters are now capturing differences between categories. Okay, so that's their corresponding interpretation. Okay, but there are in fact 3 comparisons. So we've only had the parameters directly represent 2 of them. So beta 2 is difference between semi and dry. Beta 3 is difference between wet and dry. So how would we describe the difference between what's left? Semi and wet, right? So the difference between semi and wet, well, you would actually have to take the difference of these 2 lines. So in fact, that difference you need to use both beta 2 and beta 3 in the estimates to describe. Okay, and then so beta 2 minus beta 3 would be the difference between semi and wet. Okay, holding everything else constant for the expected response. Okay, so that's how we can describe the differences in the expected response for the different categories after setting up these indicator variables. Now, the last point I want to make is concerning its. Now suppose we do the estimation, and we have beta hat, and we also have the estimated covariance matrix for beta hat. So how do those come into play when we want to compute, let's say, confidence intervals for all of these differences. Okay, so first let's write down our expression for beta hat. Okay, so the vector of betas, as we recall, has a multivariate normal distribution when viewed as a random variable. The mean is beta, and then the covariance matrix is sigma squared times matrix V, where V is X transpose X inverse. Okay, so as we already described, when we talked about this derivation, that so we know if we take an individual parameter, it's called beta j hat, as a normal distribution, beta j, and then sigma squared times v jj, right? So jj is the entry in the jth column and row. Okay, so in other words, the jth diagonal element of the matrix. And so, or in other words, the standard error for an individual parameter is sigma hat root vjj. Okay, so that was from before. Okay, so using this, we can get confidence intervals for beta 2 and beta 3. Okay, but what about for beta 2 minus beta 3? What if we wanted a confidence interval for the expected difference in flavor between semi and wet processing methods? Well, now we have to deal with this combination of two parameters, beta 2 minus beta 3. Okay, and so we can use this. Okay, so this fact helps us deal with the cases of individual variables. But what about this case when we want to deal with beta 2 minus beta 3? Okay, so what about beta 2 minus beta 3? Okay, well, in order to get a confidence interval, well, first we needed standard error, so let's write down the expression for the variance. So the variance of viewing these as random variables, so beta 2 hat minus beta 3 hat. Okay, so we expand this this variance of this linear combination, so we have variance beta 2 hat. We have plus variance beta 3 hat. Okay, so the minus 1, so squared, so we get plus variance beta 3 hat. And in general, when random variables aren't independent, then in general we will have a covariance term. So we have minus 2 covariance beta 2 hat, beta 3 hat. Okay, so now what are these? Okay, well we already talked about the variance. These variances we know they have this form. So you have sigma squared times the second diagonal element, and the variance of beta 3 hat is sigma squared times the third diagonal element. And the covariance, well, in this case we'd have to look at one of the off diagonal terms. So this is one example where these off diagonal covariance terms is going to come into play. So what is this? Well, this guy, you're going to look up remember it's symmetric, right? So you can either look at the entry in the second row, third column, or second column, third row. They'll be identical. So what is it? Well, the entry in there is sigma squared times the corresponding entry of V. So V23 or V32 be the same. Okay, so that's where that covariance term in the estimated covariance matrix is going to be useful. And so with that in mind, then we can say that the so this expression is what's going to help us get the confidence interval for the difference between semi and wet. Okay, and so with that as the expression for the variance, that means our standard error for this difference. Okay, so the value we actually calculate, well, we plug in the estimate for sigma squared. So we have a sigma, and we can take a square root. So we're going to have sigma hat and then square root of these three things coming from the V matrix. So V22 plus V33 minus 2 times V23. Okay, so once we have the estimate and the standard error, well, now we can compute the confidence interval for any of these pairwise differences, wet and dry, wet and semi, that's this one, and then dry and wet. Okay, so now we can use the estimates from our multiple linear regression model with this categorical predictor coded using indicators. And now we can interpret all the differences between the three categories in terms of the betas. Okay, so we can say then that we now have and can construct confidence interval for not just individual parameters but also for the difference between beta 2 and beta 3, which has a very interpretable meaning. The difference between two specific categories for the method. Okay, so I've illustrated this with a specific example just to motivate things. But in general, you can see that if an explanatory variable had k categories, so in general, for an explanatory variable with okay, so let's generalize and say you have k categories. And we want to give each of them a particular mean response. Then we will need to define k minus 1, so one less the number of categories as indicator variables. So we would need k minus 1 indicator to code for potentially a different mean response for each category. Okay, and so we can take one out because one of them is linearly dependent on the other. It's simply it would be 0 for all the other categories would define the final category, like we saw in this example. Okay, so that is what I wanted to cover today as far as integrating these types of categorical predictors in our regression model. And so I will pause for a few seconds and see if there are any questions before we wrap up. Okay, so I don't see any questions for now, so we will conclude today, and I'll be back on stream on Monday.